This is what you guys did in lab yesterday. You got the mass and the volume of your stopper and wind block, and you did a ratio, and you came up with the density. Okay, so density kind of says how compact it is or how fluffy that object is. So one of the things throughout working problems, not just in chemistry, in all physical science, even in biology, which is not physical science, but in all science, in physics, you should always include your units. I call it naked numbers, like if if it's 3.29 inches, you just put 3.29, that just feels so empty. It's naked, okay? It's called dimensional analysis or dimensional consistency. The units, honestly, that you get at the end of working your problem show you that you have it set up right, as long as you don't lie about your units. So a little more about the density of just picking the beautiful substance, water. So I already told you that water is unique, and we're going to see kind of a graph of the density of water. But water is densest about 4 degrees Celsius. And we're going to go with that density of the beautiful number. The density of water is 1.00. Of course, these trailing zeros after the decimal are significant. So how many sig figs do we have there? 1.00. 3. Oh, sorry. That's 3. That's 3. Okay. Now, I think I mentioned you need to commit that to memory. Okay. Density what? So graphs are beautiful. Give me a graph any day, aside from the whole blah 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 of words, right? So this is actually plotting the density of water as it transitions from a liquid to a solid. So what temperature does water freeze at on the Celsius scale? 0. Okay. So here we have 0 degrees Celsius. So we're going to kind of look at this graph from right back to left again. So can you see in its liquid phase, because here it is, Celsius temperature, it's above freezing. And as we cool down, what happens to the density? Does it go up or go down? It goes up. It becomes more compact as you cool it down. Okay, so I like that. About 4 degrees, it's got its maximum density. Okay. Then between 4 and 0, it's still a liquid, but it starts to get ready to solidify. This is so cool. It's like they're smart little molecules. Okay. So between 4 and 0, as you cool it down, what happens to the density? Does it increase or decrease? It decreases. That's right. Then when it transitions, so it kind of fluffs out. Density decreases, it fluffs out. Then when it transitions from a liquid to a solid, there you go. Is that not cool or what? So it fluffs out, it becomes less dense. But what happens as it's solid and you go ahead and you cool it down? What happens to the density there? It increases, it goes up, exactly. So the density increases here. What's this little jag right here? Some of you guys know.
Breaking the scale.
A break in the scale, exactly. Because they wanted to emphasize this part of the scale and that part of the scale, but they didn't want to keep it so elongated that it went off the charts. So actually, it's even more exaggerated. It's shown there. So this is kind of showing the same thing. Here we have water right at its boiling point temperature, cooling down to at its densest. So here, increasing density. Here we have it decreasing density, and there's a humongous jump when it transitions from liquid to solid. Oh. Okay, so we're done with the water thing for now. What this is showing you is similar volumes, but which one do you think weighs more? Styrofoam or rock? The rock. The rock weighs more. And density is a ratio of mass to volume. You might say, well, the rock is more dense. But mathematically, the rock has the higher density. So they have similar volumes. You guys told me the rock weighs more. Mathematically, it'll come out with a higher density. Okay. Makes sense. So the thing about objects is that if there's a fluid involved, objects will go ahead and be sorted based upon their densities. So here, rock is most dense, water is in between density, and styrofoam is the least dense. So this is probably going to look like a familiar problem to you. This is what you guys did with your rubber stopper, basically. getting the volume of an irregular object by displacement, which is exactly what you guys did with your graduated cylinders, plopping your stopper in there as you displace the water and you're going to get the volume. So here we got the mass of rebar, and then this paragraph right here kind of describes, it's too many words here, far too many words. I like the next slide, which is just a darn picture of this thing. This just kind of shows you that the graduated cylinder had a volume without the rebar of 13.5 milliliters, with the rebar 22.4 milliliters. So of course by difference we can get the volume. And then all we got to do is take that mass divided by the volume that we got by difference. So it looks like this, a picture, and why did I just put a picture? All that blah, blah, blah. So when you're working problems, including when you're working calculations to hand in as part of, as that second part in your semi-formal lab report, let me know if you have any questions about your semi-formal lab report. You're at a little bit of a disadvantage for this long weekend in that you don't have like Monday and Tuesday to kind of communicate. So Wednesday, if you have a draft of it and you want that floated by me, you definitely could, because I have office hours after this and before this. Okay, but beginning, well, yeah, Thursday-ish at noon-ish, I'm not going to kind of give you time to fix it. So anyway, so you always want to write down, even if you're like, I can do that subtraction in my head, we'll write it down. Okay, communicate it. So of course we can get the volume of the rebar by difference. We take the volume of the water before it was in there minus the volume that was there with the rebar, and we get the displaced volume. We don't do a lot of subtraction or addition in chemistry, not as much as multiplication and division, but we round according to decimals here. So notice we have 1 decimal and 1 decimal, so we're allowed 1 decimal. You might be like, no, it's sig figs. I got 3 sig figs here, 3 sig figs here. You do have 3 sig figs in both of those volumes. But you don't round according to sig figs, you round according to decimals. All right, so that's the number that's going to go in the denominator here in a minute. So simply the density is the mass divided by the volume. So how do we need to round this? Fingers. So this is sig figs. How many sig figs? I'm liking just 2. Yep. Round to 2 sig figs, I get 7.8 grams per mil. Any questions about that?
Like how we did it in the lab, you had to multiply each centimeter with centimeters cubed. Do you have to put 1 centimeter cubed equals 1 milliliter when you want to change it to a gram or whatever? And that's all you have to do is just put it off to the side, right? Like 1 centimeter cubed equals 1.
You are definitely on something. So what you're saying is if I have this 7.8 grams per milliliter, I know since 1 milliliter is exactly 1 centimeter cubed, I could simply go to 7.8 grams per centimeter cubed, right? Well, I'm going to get ahead of myself a little bit, and I'm going to show you, and we'll get to this a little bit today and even more on Wednesday, that actually you need to do this. You guys remember that you can unpack G/ml really means grams per 1 milliliter. Those mean the same thing. So I'm going to go 7.8 grams per 1 milliliter. And then today when we start to talk about factor label, we use equivalency statements just like this to make them a conversion back, which is just a ratio. And I'm going to put what? 1 milliliter up here and 1 centimeter cubed down here. And the units we're left with are grams per centimeter cubed, and the number is 7.8. So that's, yeah. I know it's, sometimes there's things in classes where you're like, oh, I need to talk about this, I need to talk about this, so, but this is how I'm going to see that. Good question. Okay, So another thing I want to kind of throw at you is this idea of weight percent or mass percent. And I like Lindsay's question, and can we use mass and weight interchangeably in chemistry? Right now you can. Okay, even though they aren't the same thing, I know. So mass percent or weight percent of any component, by definition, means it's the grams of that component. By the way, if we're talking about weight percent, we must be talking about a mixture, because you have multiple components kind of physically tossed together. So by definition, a weight percent means grams of that component per or over 100 grams, exactly 100 grams of that mixture. That's what I call unpacking. That's how you would unpack a weight percent. Call that unpacking. We see them all the time. Let's see. So this is unpacking. Are you serious? Let me try this. Try this. So this slide is talking about unpacking. So for instance, you see weight percents all over the place. For instance, here is a bottle of Clorox, and you can find listed, oh, thank you. Oh, eagle eye there. Right here. Contains 7.4% sodium hypochlorite. So what that means is that there are 7.4 grams of NaOCl per 100 grams of solution, which in this case is the solution is the stuff in the jug. The solution is the Clorox. Okay, this is unpacking. Now I mention that, I emphasize unpacking, blah, 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 because sometimes you're going to need to take that weight percent, and if you're going to use it in a problem, you can't use it in a problem as percent. You have to use it in a problem. Oh, see there. All right. So that's how you unpack. That's by definition what weight percent, mass percent means. This is how you calculate mass percent. There's a good chance that you don't have 100 grams in your substance. You have some random grams of your substance. So basically, you isolate a blob, you get the mass of that blob, and you put it down there. You get the mass of your component A, and you put it up there. Okay, so your component A is a subset of your mixture. To get it to parts per 100, you have to multiply that decimal number by 100. And that would be your parts per 100. That's called mass fraction, mass percent. That's how you calculate it. I added a little bit to this slide. Actually, the blue and the white there were not on the slide before. If you're like me, I got mass fraction. I got weight percent. I got mass percent. That makes sense to me. But kind of a step right before this is something called mass fraction or weight fraction. And if you look back and forth between this blue box and the other blue box, the things that's different is it doesn't have times 100%. So simply, you take your blob of mixture, okay, that whatever that mass is goes here, whatever the mass of the component is goes there, okay, and voila, you'll have a decimal number, and that's the mass fraction of component A. So mass fraction times 100 is mass percent. Feels like we just kind of go in circles here. One more thing I'm going to add, if you were to unpack, mass fraction, it means grams of component A per 1 gram of mixture. That's what it means. So a little bit ago, that 7.4%, what is it, NaOCl? Sorry. Does this make sense? That mass fraction would be 0.074 mass fraction. NaOCl. That make sense? And then by definition, what that means is I have 0.074 grams of the component for exactly 1 gram of the mixture. Sorry, that's getting kind of sloppy there. I'm liking my pen is behaving when I push down on it better. So let's do an example where we have a sugar solution, and we're going to go ahead and knock out both mass fraction and mass percent. A lot of times, and I doodle, I call it doodling, and it's kind of killing time. I like chemistry problems sometimes where you can draw a picture, and this picture looks like this. We have 5.42 grams of sucrose, and I am going to add them to 28.72 grams of water. You know, do you have to draw the picture? No. But is it like stalling? Yes. And sometimes you're like, oh, okay, I'm going to physically toss those together, make a solution, make a mixture. And then the question here is in italics. Determine the mass fraction and the mass percent of sucrose. So mass fraction is going to be number of grams of sucrose divided by total grams of solution. That's it. Mass fraction. Mass of sucrose divided by mass of solution. Now you can see that I've done the mass of solution kind of as a side note over here. You could actually just go ahead and slap it under the denominator if you wanted. This sort of idea of just taking this a little simple addition problem, though, aside, instead of kind of balling it in with your ratio, gives you a little more confidence that you're going to round correctly. So we need to round according to what? 2 decimals, since we're adding 2 decimals here, 2 decimals here. So the thing that's going to go in the denominator for our mass fraction, for the total solution mass, is 34.14 grams. A really common mistake is to say, oh, Mrs. Snipes said sig figs. Round according to sig figs. No, you're adding, so it's decimals. Now we're ready to go ahead and take a ratio. In the numerator is going to be the mass of your sucrose, 5.42 grams, and the denominator is going to be the total mass of your solution, 34.14 grams. Don't forget to, it's not just grams, but it's grams of what it is. Another thing I guess I like about the picture is you're less likely to get it wrong. If you draw that simple picture of the beaker with the fluid, you draw what the fluid is, you draw an arrow, what the in this case sucrose is, okay? So, I should have had you have a show of hands, but you see where we have 3 significant figures here, is what we're allowed. Okay, so 0.159, that would be mass fraction, sucrose. So I'm all about units, and you'd be like, well, Mrs. Snipes, on your answer key, you didn't have units. Well, I allowed the units of grams of sucrose and grams of solution. I allowed those 2 units to cancel. Grams and grams cancel. So mass fraction is unitless. And I talked just a minute ago about unpacking a mass fraction. What does that look like? Well, if somebody says it's a mass fraction, then that must be the grams of the component per 1 gram, exactly 1 gram of the mixture. We've talked about exact numbers either by definition or counting. Okay, this is by definition. So that one there is exact because you unpacked it that way. That's exact. All right. So mass percent, we could go through the process and put the, what would we do? We would put the mass of sucrose over the total mass of solution. And then how would this one be different than the mass fraction? What would we do different to get mass percent? Yep, multiply by 100. Exactly. So I'm not going to belabor that for you. If you take 0.159 times 100, you get 15.9. Okay. Then I'm trying to think, now if I was a student, my teacher said, for this sugar solution, give me mass fraction and mass percent, how would I, once I have mass fraction, how would I say, so mass percent is this? I don't know. Because I just kind of jumped to it. I would rewrite this just for kicks. So what 15.9% by weight means is this. There are, by definition, what percent means, that's parts per 100. So that means there are 15.9 grams in this case of the component, sucrose, in 100 grams of the solution. Like our one was exact, this also is exact. That's by definition. That's what the percent means. All right. Maybe we'll get through the next part. Now, just so we're all on the same page, I wanted to kind of remind you, I thought we'd take one more look at Canvas right quick. I'm going to get to it, and then we'll... I wonder if... No, that won't work. Oh, there it goes. That's a good sign. In the grade book, I like the grade book. I like the grade book. It kind of shows your attendance, but your attendance isn't factored into your grade. The one thing, though, is it can give you false security about doing real well in the class, like you have an A now, or like not doing real well in the class because it's been hard to get a few assignments in. But please know that you can check your grades, and I'm keeping up with my grading my homework. So. Don't forget then, I'm going to take you to the modules. Under the modules, oh, by the way, that first homepage is, like if you miss a day, you can see here, click on this link. These two links for lab. This link right here, Wednesday's lecture, you can click on that link and it's a YouTube video, and you can see what we did in lecture. But under modules, okay, under modules, if you go to, HW stands for homework. So I'm going to open this homework unit 1, Gen Chem 1 OpenStax. So, and that's the document you might be referring to, but just in case you lose it, this is what homework is due. So you don't have an excuse for not having it. Okay, so this is the homework you guys have handed in so far. What are we up to? Part 4? And I mentioned that because notice that Part 4 has some, you do 8.7 and 8.8 from your textbook, and then there are some additional problems. So don't feel too bad. You'll have a little bit to do over the weekend, long weekend. Okay. And then, as crazy as it sounds, because it still sounds a little crazy to me, if we go back to the modules, there is that famous Homework Solutions tab right there. So if you click on Homework Solutions, okay, let's see, we're going to do 4. Here are, no pun intended, here are the solutions to 4. Like, oh, don't show me. Okay. I would probably use these to check or if I got stumped. But you can see that I worked them all. Okay. So, and there's the answers to the ones you're handing in today, etc. I figure you're all adults. You know, you can do with them. Are there any questions about all this? So yeah, that's all available for you. And the little red thing, ugh, the little red thing means that I have to optimize it for, like, if somebody needs a reader or something. I don't know. Anyway, I don't think it's red on yours. So keep me posted if you have any questions. So let's go on to factor label. See how far we get. That's all good. Oh my gosh. This one. So just like significant figures is a way of rounding problems, and I tried to show you why we have the rules of rounding that we have when it comes to measured quantities with uncertainty are all certain in the rightmost digit, and you have to see how that uncertainty propagates through. So I kind of tried to convince you of that. That multiplication, division, you round according to sig figs, addition, subtractions according to decimal places or places of 10. But just like that's here to stay, so this is also here to stay. This is the factor label method of working problems can save your butt. Even if you don't know what you're doing, as long as you make sure your units work out, you're gold, okay? So it works very well in physics, and it works very well in chemistry, and I don't know about biology. It probably should. This is a figure from your textbook that has the metric prefixes. And what I want to draw your attention to is kind of that last column. This last column. These are a bunch of equivalency statements. Remember, as I'm doing this, I'm like that kind of pan balance. Right here's the equal sign, and these are equal amounts. These are a bunch of equivalency statements. Do you guys remember which 4 you need to know for your test? Which one? I like micro, milli for sure. Not nano. It's a cool one, but you don't need to know it. 2 more.
Centi and kilo.
Centi, yep, and then the big one, kilo. Those 4. Yep. So know those 4. Doesn't mean that, like, to work a test that you won't have to know all some of the other ones. Equivalency statements. More equivalency statements. Which of these do you need to commit to memory? The first one, exactly. That's it. You have to memorize that. 1 inch is exactly equal to 2.54 centimeters. Every once in a while, I'll get that turned around. 1 inch exactly 2.54 centimeters. All right. Need to memorize this one? Yeah. So equivalency statements, and we're going to see that equivalency statements are our way of getting down the road to a general type of problem called a conversion problem. Equivalency statements are a way to convert from this unit to this unit. We use an equivalency statement. So they're not in order, but these are, broadly speaking, 3 rules of working problems using the factor label method. The first is no naked numbers. Okay, so you just can't have a floating number without a unit. Okay, always include your units. So this says, those equivalency statements we've been talking about, this says you're going to take an equivalency statement and you're going to make something called a unit factor or conversion factor. Let me kind of jump ahead and show you what that looks like. Let's just say A is equal to B. It could happen. Okay, A is equal to B. That's an equivalency statement. Your 2 possible unit factors, and I'll show you why this is, are going to be, it's going to be a ratio of either A over B or B over A. Okay, those are your 2 ratios. Those are your 2 conversion factors, unit factors from one equivalency statement. Okay. The last thing is that you're going to choose the left one or the right one according to how you want your problem to go. Okay. You're going to choose it, the conversion factor that came from your equivalency statement. I hope you're not. I hope you're doing this.
Do what? I was playing with canvas.
Okay. I was like, he's laughing back there. I'm like, I'm not saying anything funny. So you're going to use one of these two to get you down the road. And I'll show you what I mean by that. And you're going to use it such that units in your first term cancel, and you get at least towards your final goal. So it looks like this. If I were to ask you, like, 2.5 feet, how many inches are there? You'd be like, well, 2 feet, see, 1 foot, there's 12, 2 feet, there's 24, half a foot, there's 6 inches, right? So 24 plus 6 is 30, right? 30 inches and 2.5 feet, and that's cool, but that's too easy. We're going to take that one example, and I'm going to show you the simple example, and it's good because you know the answer. Let's go ahead and take 2.5 feet and convert it to inches, and this should be what we come up with. Well, to start down the road, to convert from, in this case, feet to inches, we have to come up with some relationship. Now, this is a nice direct relationship. Usually, it's not always this obvious or this direct. We clearly know that by definition, within the English system, 1 foot is equal to 12 inches. Okay, we do know that. Is that an exact relationship? How do people think that's exact? No? What? Why is it exact? It is an exact relationship. Somebody tell me why? Because we know that. We English people, those English people set it up that way. Exactly. We know it. It's by definition. That one is exact, similar to, like, you guys would tell me there's like 1,000 meters in 1 kilometer. 1,000 meters in 1 kilometer. That's also exact. That's by definition with the metric system. This is by definition with the system. Yep, that's exact. So kind of like you saw me before, we can go A over B or B over A. Okay? So let's do this whole 12 inches over 1 foot. Oh, oh, duh. I'm sorry. I'm drawing a blank. Oh my gosh. Okay. So one of the things we know about equalities like this is like you see in this here. We can go ahead and divide both sides by 1 foot. I'm like, that looks so foreign to me. We can divide both sides by 1 foot, and we have not changed anything. Okay, so we have 12 inches divided by 1 foot, 1 foot divided by 1 foot. What's 1 foot divided by 1 foot? 1. It's just 1, yeah. Yeah, 1 foot divided by 1 foot is 1. Okay, yep. So that goes to form 1. So here we have this ratio of 12 inches over 1 foot is equal to 1. And is it the identity property of multiplication of 1? If you take 1 and multiply it by anything, you haven't changed that number. Okay. So here's a cool thing. We can take this ratio and insert it into stuff that's being multiplied out. And that's just like inserting a 1 term. Isn't that cool? So the other thing, we could go back to our 12 inches over 1 foot, and instead of dividing by 1 foot, we can divide by 12 inches, and it looks like this. 12 inches over 12 inches equals 1 foot over 12 inches. That's legit. So of course, 12 inches over 12 inches is 1. So here we have 1 is equal to 1 foot over 12 inches. Okay? So when I talk about kind of the two ratios, you know, A over B or B over A, that's exactly what we have there. We have two options of the relationship between feet and inches that are are 1 that we can go ahead and insert as we need to. Okay? So if you would, we're going to call this A and we're going to call this B. Now it's not A, okay? The first one's A, the second one's B. So now let's go ahead and work the problem. So what I usually do is the first term, and sometimes I run students who do this like backwards from me, but what I usually do is my first term, I take the thing I want to convert and I put it over 1. I know it doesn't say that in my notes, but that's what I usually do. 2.5 feet, we're trying to get inches. 2.5 feet over 1. Now, what do you think, A or B? Because I want feet to cancel and I want to be left with inches. So look back to the previous slide. How many people think I'm going to use the A ratio? How many people think I'm going to use the B ratio? A it is. So if we go ahead and insert this ratio, which is the relationship between inches and feet, and it's 1 we decided, okay, we can go ahead and now our units of feet will cancel. And we're going to go ahead and cross those out. Sometimes I get sloppy and cross them out. Then we have units of inches. This is what I said, as long as your units make sense as you work your problem, then you're in good shape. All right. So we know our units are fine. Now we're ready to worry about our numbers. So the numbers we have are 2.5 and 12. So we multiply that out. Now I told you, or you guys told me maybe, that there is no uncertainty introduced by that 12 inches over 1 foot, because that's an exact relationship. Is there uncertainty in 2.5? Yes. How many sig figs in 2.5? 2. Very good. So we need to show 30 with 2 sig figs. And that's why, showing 30 with 2 sig figs, I've done it this way. So that decimal is not just like an end of a sentence or something like that. That is not a period, it's a decimal. So that is, remember, the fact that there's that explicit decimal there means that this is significant and this is significant, and we have our 2 sig figs that you guys told me. Okay, so that's how that works. You're like, well, I knew it was 30, but... And then that actually, I don't know if that kind of makes even more sense, but this was a good example Lindsay was asking about. Because she's like, you guys know that density can either be grams per milliliter or grams per centimeter cubed, and you know that the relationship between milliliters and centimeter cubed is 1 to 1. So you know that numerically it's going to be the same number, you can just change it. But I'm here to tell you that if you want to make that leap, I'm going to have you do it this way, 7.8 grams over 1 milliliter. And I want to get centimeters cubed here, so I'm going to put 1 milliliter in the top, centimeters cubed in the bottom. And there we have done it legitimately. So we went with A. If we'd gone with B, this is where you're like, all right. So if we had gone with B, notice our number would have been different, 2.5 divided by 12. But notice that nothing would be canceled, and we'd have units of what? Feet squared per inches. You're like, that's not right. Okay. Cool. Let's do another one, shall we? So you're supposed to memorize the relationship between inches and centimeters. So what is it?
2.54.
2.54. Okay, let's go. Yeah, centimeters per inch, exactly. So you guys know that. We could kind of diagram how we're going to do this, and it looks sort of like this, kind of like you read a chemical reaction from left to right. This is showing you the flow of how you guys are going to do this. We can get from centimeters directly to inches using what you just told me. Using 2.54 centimeters is equal to 1 inch. Exact, right? No uncertainty? So the first term is going to be the thing we want to convert, which is that 5.52 centimeters. And again, in my notes, I apologize, but what I would do is put it over 1. Put my little things, get all warm, fuzzy feelings. So what term do you think, how can we use this equivalency statement now as a ratio to have units of centimeters cancel, be left with units of inches? Yep, multiply it by 1 inch over 2.5%. Perfect. Units of centimeters cancel, we're left with units of inches. That's awesome. So we have the units are great. I just focus on the units and then I go back for the numbers. So number-wise, in our calculators, we're going to take 5.52 divided by 2.54. So is there uncertainty brought by the 5.52? Yes. I'm going to go ahead and put little check marks. I'm liking, you guys would, I'm sure, tell me 3 sig figs. How about the 1 in 1 inch? Nope.
How about the 2.54? No. Think about it this way. It's by definition. It's the weird one that's by definition. There would be 3 if there was uncertainty there, but there's no uncertainty there. Nope. So we're not going to let it limit us. I bet next time I ask, you'll be like, okay. Does that make sense, though? Okay, so how do we need to round our answer? Yeah, 3 sig figs. Yep.
So I get 2.17 inches. And a lot of times problems, chemistry problems, physical science problems, like, well, does that make sense? Yeah. So just, all right, let's do another one. Now you needed to memorize the previous relationship. Bless you. But did you need to memorize this relationship between ounces and grams? Yes. Okay. So if you look back a few slides, or is this the one? Yeah, we're going to go through a few slides. If you look back a few slides, I have grams and pounds, but I don't give you ounces, grams to ounces. Okay? Do you guys know how you can get from ounces to pounds?
There's 16 ounces in a pound.
Yep, 16 ounces a pound, exactly. So this is an example where we're actually going to have to do 2 ratios. Okay. Are you done writing down or? So we got it. Okay. So, and then we can go from pounds to grams in this thing that I never memorized. 453.6 grams is equal to 1 pound. Okay. So this one right here, is that exact? Yes, it's exact. So I'm going to go ahead and put X's there. It is exact. What about this one right here? Is that exact? Nope. It's approximate. We're not going to, our 1 is not going to mess us up, but we're going to have to only allow 4 sig figs in the 453.6. Exactly. So we're going to work this like we worked before. Our first term is going to be the thing we want to convert, which is our ounces. So we'll put 2.75 ounces over 1. So now go ahead and use this equivalency statement. How can we use it to our advantage to make ounces cancel, left with ounces cancel, left with 16 ounces in the top or bottom?
Bottom.
Yep. 16 ounces in the bottom, 1 pound in the top. Perfect. How about this equivalency statement, making it so our pounds will cancel?
You want the pounds on the bottom?
Yep, pounds on the bottom, plus you, 453.6 grams on the top. Exactly. That's it. So, no uncertainty brought here. We said there's 4 sig figs here. What about this first term? Is there uncertainty in 2.75? How many people think there is? Yes. Why is there? Did you say yes? Yeah. Why? You're right. It's uncertain. It's an estimate. Somebody says, I have a volume here. It's 2.75 ounces. It's probably 2.75 ounces plus or minus 0.01 ounces. Probably. There's uncertainty there. Yep. So there is uncertainty, 2.75 ounces. So how many sig figs? 3. Okay. So how we need to round our answer? 3 or 4? Like in 3. Yep, you got it. So sometimes I assume this, but I shouldn't. Now, what you can do, there's a couple ways to work this. We have numbers of 2.75 in the numerator and 453.6 in the numerator, and we have one number in the bottom, just simply 16. So you can use the parentheses in your calculator, like open parenthesis 2.75 times 453.6, close parentheses, hit the divide by key, enter 16 and equals in your set. Some students prefer to kind of take the 2.75 times 453.6, write it down, and then go ahead and take all your stuff in the bottom and write it down. So either way. You guys told me 3 sig figs, and I agree. So to get 3 sig figs out of this, and I can't remember what the raw number is. What was the raw number? 77.96. Thank you. 77.96. If we want 3 sig figs, we're going to keep those first 3 digits from left to right. So we have to truncate it here. And since that's a 6, that rounds the 9 up to a 10. And then that rounded that up 7 up to an 8. So 78.0. Excellent. Okay. Well, I think that's a pretty good place to start. We got down the road with working factor label, and you probably could do some of these part 5 if you wanted to. But that part we finished today is due on Wednesday. No class on Monday. Okay.